Okay. Good afternoon and welcome to MAE 106. This is Discrete Mathematics with Probability. My name is Richard Kowar and this is going to be lecture 29. I hope everyone can see and hear everything okay. If so, just say so in the chat. Good. I like to make sure everyone can hear me okay. Excellent. Excellent. So just an announcement, because we have test 3 that's coming up on Friday. And again, it's posted on Moodle which lectures and assignments are covered. But the interesting thing is that in addition to the 1 8.5 by 11 cheat sheet, you'll have a calculator. So you're allowed a non-programmable calculator. And again, this is not your cell phone. While it does have the app for a calculator, because that allows for unauthorized communication. So a non-programmable calculator and that should help then with doing some of the calculations. If you have questions about if your calculator is allowed, you can feel free to send me an email. Okay. Is everyone okay with that? Just in the chat, I'll just pause for a second and see what people think. Good to know. Excellent. Yes. This is in keeping with the other sections. Okay. Okay, so let's start into random variables. And I kind of had this quote. It was from Donald Rumsfeld. He was giving a press conference during the Bush administration, and his quote was, "We also know that there are known unknowns. That is to say that we know there are some things we don't know." And I kind of feel that what he was trying to illustrate during his presser was the idea of a random variable. Perhaps he could have also said, we also know there are random variables, and that is to say that we know there are some things we do not know. So this kind of follows 9.2 in the textbook. So when we perform an experiment, we might not be interested in the details of the outcome, but that's to say that we're only interested in some numerical quantity that's determined by the result. And by that I mean, if we consider, so the experiment is, let's say we're going to throw 2 dice. We might not be interested in the actual outcome. So, for instance, the outcome could be 2, 4. Instead, we might want to know the sum. So in this case, it'd be like 2 plus 4, which is 6. So, for instance, like I'm talking about throwing 2 fair dice, and really what I'm thinking of is craps, the kind of dice game where you throw 2 dice and you bet on what the sum of the 2 dice is going to be. So what we need, instead of writing out what we need to have some sort of notation to express where we have like the sum of the 2 dice, or trying to come up with some sort of numerical value for this outcome. And that's where we get the idea of a random variable. So here's the definition of a random variable. So what it does is assigns a numerical value Oh, maybe I should be very careful about this. So it's just, we'll say a numerical value to the outcome from the sample space. So for instance, let's say that we want to do, I just maybe put a box around this. So for this experiment that I keep talking about here, I could actually define a random variable x. That's a good question. A TI 84C. Okay, sorry, the question is this. Somebody's just asking this in the chat. Okay, So, okay, let me just switch over to my screen. So here's my screen. And this looks like it's quite a powerful calculator. It's got graphing abilities. It has, and in some cases, some even has Python, which is a programming language. So just going back to just what I had written up here, you're allowed to program a non-programmable calculator. This is that's quite a powerful calculator. So what I'm more thinking of is like a Casio 991, which would be something like this. And there's something like that one, which is non-programmable. It's a scientific calculator and allows you to do kind of just calculations, something like that. Okay. And people are going to keep asking me different calculators. Okay. So I'll just have a quick check. Yes, something like the Sharp EL 531 looks non-programmable, so that's fairly straightforward. And you know, something like that. Oh, sorry, what's the XL? Not sure if it's showing up. Anyways, if you have any questions about that, feel free to send me an email about it. Again, just as long as there's nothing programmable in it. Yep, perfect. Just send me an email. Okay, so just going back to this experiment, we're throwing 2 fair dice. So for instance, we could say that we're going to have a random variable. So we'll let x be a random variable. That is the sum of 2 dice. So what that means then, that if I have some sort of outcome, like 2, 4, then what we would do is that random variable would be x is equal to 2 plus 4, which is 6. If I had something else like 1, let's say 3, what do you think that value of x should be? That's right, it should be 4. Okay. So, why was I being very careful about when I was defining what a random variable was? So I had initially written real in parentheses, but I don't want to put that there. I don't want to confuse people, because what we end up actually having is there's such things as we'll have discrete random variables. Okay. And so what this does is it would be a random variable that assigns get ready for it, discrete values. So discrete values meaning that it can be a natural number. So here's the natural set, which we had seen previously in set theory. You could have the whole numbers. So let me just write over here, we'll have natural numbers. Here are the whole numbers. So you can think of that as 0 union with the natural numbers. This is a Z or Z, and these would be the negative numbers with 0 and the positive numbers. Those are called integers. And that's where you will have both the whole numbers that are both positive and negative. Maybe just over here, we'll just have a little diagram. So here I can draw, here's the natural numbers. Let's have a universal set here. Then I can have, let's say, something over here. This is the whole numbers, and even bigger. There's the integers. So again, that's just illustrating that the natural numbers is a subset of the whole numbers. And again, that's a proper subset because there is at least one element more in the whole numbers than in the natural numbers. That specifically is 0. And the integers is a proper subset, or sorry, the whole numbers is a proper subset of the integers. So the natural numbers is a proper subset of the wholes. The wholes is a proper subset of the integers because, again, there's all these elements here, the negative numbers, that aren't in the whole numbers. So that's what we call a proper subset. So that means when we're thinking of discrete random variables, it's a random variable that assigns discrete values. So these are kind of, not decimal numbers. The other ones I should also mention is that the rational numbers too. So the rational numbers are these are called the rationals. And that's where I have two numbers that are in a fraction form. So I can have like m and n, m over n, such that m and n are integers. And let's make sure that this is defined properly so that this doesn't crash. So we'll say that the denominator cannot be equal to 0. Okay. So those are called discrete values. So when we look back over here, this is a discrete value, a discrete random variable, because I have 2 plus 4 giving me 6. an example of a random variable, of a discrete random variable. Okay. Let's go over here. We can do continuous random variables. So over here, it's a random variable that assigns real values. A random variable that assigns real values. And by real, I don't mean like I mean it in the mathematical sense, as in the reals. So again, it's very hard for me to express it as a set, but what I can do is I can show like numbers that are pi would be part of it. It would also include all the integers. It also include all the rationals. And let's say that I'm going to call this basically Q complement. And what that is, so over here I would have the rationals. And over here is what I would call the irrationals. So if I kind of wanted to express this as a set, the reals is the union of all the rationals. So that includes then the integers, the whole numbers, the natural numbers. So it's all those counting numbers or the discrete variables. With the irrational. So again, irrationals numbers that can't expressed as a fraction. You know, things like we have square root of 2, square root of 3, square root of 5, and so on. Those are numbers that we can express as a fraction. So there's two kind of main types of random variables. We have discrete and we have continuous. And in this course, because we keep saying that this is a discrete mathematics with probability course, we'll be focusing on discrete values. But let me just give you some examples of what a continuous random variable would be. Something like something that we kind of measure. So we can have like length of time for a phone call. Could do the height of a person. Could do the amount of coffee that's been poured into a cup of coffee, or a cup. Poured into a cup. Basically, some sort of measurement that has a lot, in fact, an infinite amount of precision. Okay. So let's go back to that example of the dice. Oops. So let's go back to throwing the 2 fair dice. And so we can have our sample space. We have quite a bit. We can have like 1, 1, 2, 1, 3, so on and so forth. Okay, that's, by the way, how many outcomes are in that sample space? How many possibilities are there? Just in the chat. Yes, 6 squared, 36, good. Yes, exactly. So for the first die, there's 6, and then for the second die, there's another 6. You can do 6 squared. Exactly. You can have 36. So that's quite a bit of writing. So I'm not going to write all of them, but what we are actually interested in is, let's say that we'll let x be the random variable. For the sum of 2 dice. So what values can x be? What values could x take on? What do you think in the chat? Exactly, 2 through 12. So x could be, I'll just write it as a set. It could be at 2, 3, 4, all the way up to 12. Again, the smallest one that we can come up with was 1, 1 for the outcome. Over here, this would be 6, 6. And what I'll do then is I'll do a little sum table. So we can have 1, 2, 3, 4, 5, and 6. So this is for the first die. We'll have the second one go down here, down this column. Okay. So then if I add them up, 1 plus 1, there's 2, 3, 4, 5, 6, 7. I just shift again, so I'll have 3, 4, 5, 6, 7, 8. 4. So I'm just writing out the sum table for this. Okay. And so you can see the ranges. The range is from 2 to 12. So there's the minimum and there's the maximum. So you can see that the values, there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yes, it does go, if I do sum up the 2 dice, the possibilities are 2 through 12. Okay. So when I write, for example, x equals 6, over here, this means that I could have the possibilities of, I could have 5 and 1. I could have 3 and 2. I could have 2 and 3. And I can also have 1 and 4. Oh, wait, I'm not following that correctly. Sorry. Four and 2. There we go. Yes, thank you. 3 and 3. 2 and 4. And lastly, 1 and 5. Okay. Now what ends up happening is that people aren't necessarily interested in just the random variable per se. What they're interested is, let's say, what is the probability what is the probability of the sum of the 2 dice is 6. So what they're saying here is they're not so much looking at just the sum of the 2 dice, but now they're looking at the probability. So in notation, what we would write then is right here, here's the sum is 2 dice, sum of 2 dice, so we'll say x equals 6. And this part right here is what we would say then is p. We'll say that probability. So we can write it like this: the probability of x equals 6. So you can think of x equals 6 sort of like an event. And if you think of it as an event, you can think of it as the number of outcomes where x equals 6. So in this case, you can think of it like this. You can think of the set, which is 5, 1, 4, 2, 3, 3, 2, 4, 1, 5. All over the sample space. So in this case, there's 1, 2, 3, 4, 5, as Stephanie's pointed out. And there is, from the original sample space that we're working in, which was 36. And we can do this for each of them. All I have to do is go look up here. There's only one outcome, 1 and 1, which gives me that. So this would be 1 over 36. I could look at when this random variable is equal to 3. So in this case, I look back up here, and there is 2 cases. So that's 2 out of 36. I have the probability of x equals 4. Let's switch colors. I'll use here. In that case, that's 3 out of 36. X equals 5. So I can pick a different color, something that people can. Blue. Let's use blue. So there's 4 cases. So again, that would be 4 over 36. I have this one up here. So let's write this down for completeness. You can see 7. There's 1, 2, 3, 4, 5, 6. So 6 over 36. Okay. So over here you have 1, 2, 3, 4, 5. 1, 2, 3, 4 for 9. 1, 2, 3, 4, 10. 1, 2, 2. And lastly, just 1 over 36. Okay. So what we've done is we've calculated then the probability for every possible value of that random variable. And this is what we call, when we do something like this, this is the probability distribution of a random variable. And so you can express this as a table. You can express this as a formula. And you can also express it as a graph. So, like what we have up here, we basically have a table. We have a table of all these values. So, for instance, I could do something like over here, I could write the probability of x equals little x. Oops, maybe instead I'll put it down below. So we'll do little x, and then below we'll do the random variable is equal to little x. So I can have my values. I can have 2, 3, 4, 5, 6, dot, 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 all the way up to 12. And so you would just write out what those values would be. So the value for 2 was 1 in 36, 2 in 36, 3 in 36, 4 in 36, 5 in 36, all the way up to 1, and then it will start decreasing back down to 1 in 36. So you could express it as a table. There's a formula you could express it as. But let's express this also as a graph. So here's the little value of x, here's the probability. So I'm labeling my x and y axes. So I can have it at 2, 3, 4, 5, 6, 8, 9, 10, 11, and 12. Okay, so and over here I can have 1 in 36, 2 in 36, 3, 4, 5, and 6. So again, if I look back at my table, I would start at 1 over here. So just draw a line with a little circle on top just to make sure that I show that this is just for the value of 2. It's not connected to any value between 2 and 3. So I just go to the next value. Here's 3. It's at 2 over 36. Same thing for 4. Here's 5. Oops, I'm smudging it. And once you get to 7, it starts to decrease again. Okay, and I'll just draw little points, little hats for it. Okay, so that's what we call the graph of the probability distribution at fix. So you can see right here, if you were going to bet, you would want to bet on something like this. This has the highest probability. Is to roll a 7. And sadly, the smallest probabilities is rolling 6 and 6. Those are called boxcars. Or rolling 1 and 1, or snake eyes. Okay. So this is the probability distribution. The one thing to notice about this is that when you're going to so if you state and sort of like using a table, a formula, a graph. So if you state the probability distribution, of a discrete random variable, all the probabilities must sum to 1. Okay. So in mathematical notation, what I'll write is this. So this is a sigma. That means sum. We're going to say all x, so that the probability of x, the random variable x taking on each little value of x, is equal to 1. So I've stated it in words. So all the probabilities of the discrete random variable must sum to 1. There's that way. So this is important. So it's a property or important property of a distribution, probability distribution. So if we want to check to make sure for our probability distribution that we've just done now, what we need to sum up the probability of x equals 2 plus the probability of x equals 3 plus the probability of x equals 4 9 plus x equals 10 plus x equals 11 plus x equals 12. So again, you just write them out. You would have 1 on 36 plus 2 and 36 plus 3 and 36 plus 4 and 36. So, oops, make sure I don't write 56, it's 36. So just looking at the graph, what I'm doing is I'm just going to keep incrementing that fraction all the way until I get to 6 and 36. And then at that point, it starts decreasing. So 5 and 36, 4 and 36, 3 and 36, 2, plus 1. Oops. So you should be able to see that. And if I add them all up, 1 plus 2, oops, shoot. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21, plus 5 is 26, plus 4 is 30, plus 3 is 33, plus 2 is 35, plus 1 is 36. So I get 36 over 36, which is equal to 1. Okay. Now, let's go back to let's do page 5. Now what we were dealing with was things like, in that case we did the probability of x equals 6, and we flip back to our previous page, we had 5 over 36. But we can also ask questions like, let's do the probability of the sum of two dice is less than 5. So in words, let me just express what this is saying. Again, we're still working with x. So x is the random variable. Of the sum of two dice. And so what this is saying is then the probability of the sum of two dice less than 5. So do people have an answer for this one? Does anyone know in the chat what it would be? Just some guesses. Six and 36. Okay. I don't know. Might be 5 and 36 again. Okay, well, let's think about this. So what we want is the probability of x less than 5. So in this case, it would be all these values less than 5. So that would be it'd be 2, 3, 4, and that's it. So it would be the probabilities of where x equals 2 plus the probability of x equals 3 plus the probability of x, yes, x equals 4. Okay, so yes, if we go back to, we can even look at the graph. We could look at the graph, which we just did, or I'm just going to use the table because I can fit this all on the screen at once. So again, probability of x equals 2, or the sum of two dice, is 136, plus the probability of sum of two dice being 3 is 2 and 36, plus the sum of two dice being 4, the probability of that is 3 and 36. So what we can do is then we can add this up. So you have 1 plus 2 is 3, plus 3 is 6. And I can actually write this in reduced form. So that's 1 over 6. Because 36 divided by 6 is 6. So again, dividing the top and the bottom by 6 gives me 1 over 6. Okay. So again, I'll write this out in words. The probability that the sum 2 dice is less than 5 is 1/6. So we can ask questions like that. Similarly, I could ask the probability of x greater than 10. So then again, we would translate that as it would be the probability of x equals 11 plus the probability of x equals 12. Because again, those are the numbers where x greater than 10, so that's 11 and 12, right? So over here, the probability then would be, looking back at our chart, we had 2 in 36 and 1 in 36. So that's 3 over 36. And just reducing this, dividing it both by top and bottom of 3, you get 1 in 12. So I will write that out then. This would be that the probability the sum of 2 dice is greater than 10 is 1/12. Okay. And just be very careful. Again, some people do mix up with the greater than sign with the greater than or equal to sign. So let's do, just push this up here. Let's do C. The probability of x greater than or equal to 10 so that would include 10 then in this case. So I would have 10, 11, and 12. So that would include the probability of the 2 dice being 10, the probability of the 2 dice being 11, plus the probability of the 2 dice being 12. So you would get 3, 36, 2 and 36, 1 and 36. So there's 3 plus 3 is 6. 6 over 36 is 1/6. So again, there is a bit of a difference. So just be very careful when you're looking at your inequalities. This is a greater than, and this is a greater than or equal to. So then if I read this out, or if I write this out in words, the probability that the sum of 2 dice is greater than or equal to 10 is 1/6. And lastly, we can do 7 less than, we can have x greater than or equal to, let's do 10. So over here, what we were looking for is the values, then, not including 7, but 8, 9, and up to and including 10. So I would just add those up. The probabilities of it being at 8, probabilities of 2 dice being 9. And again, just going back to our distribution, just our graph. I'm starting at 8. So 8 was at 5 and 36. So again, 5 and 36 plus 4 and 36 plus 3 and 36. So 5 plus 4 is 9, plus 3 is 12. And dividing this by 12, this by 12, to get 1 over 3. So again, I would just write this out as the probability So the probability that the sum of 2 dice is greater than 7, but less than or equal to 10 is 1/3. Okay, so let's do another example. Let's not do COVID tests. That takes a little bit. Let's use 3 fair coins. Okay, so then the experiment would consist of flip 3 coins. Okay, so then you would have something like the first coin could be heads or tails. The second coin, you can have heads or tails. Over here, you can have heads or tails. For the third coin, And we can also have the outcomes. So what we've seen here is we can have 3 heads. You can have head, head, tail. You can have head, tail, head. Head, tail, 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 head, head, tail, head, tail, 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 head, and lastly, tail, tail. There we go. There's my sample space. So without even counting that up, over here, I would expect I have 3 coins. So that should be, and then I have 2 outcomes for each. So again, there should be 2 to 3, or there should be 8 outcomes. 1, 2, 3, 4, 5, 6, 7, 8. Good. Now, what I'm going to do is I'm going to say let x be the number. Ooh, and I gotta be careful. It's not just the number. Let's say let x be the random variable of the number of heads that appear from the 3 coins. Okay. What I can also say then is let's do this over here. Let y be the random variable of the number of tails then. Let's do tails. Okay, so let's do that. So what I would do, again, the random variable is simply mapping a number to the outcome. So what I would do is I've written out all my outcomes here. And what I'm going to do is I'll write over here, I'm going to do x. So here's my outcomes, here's x. So if I look, x is concerned about the number of heads that appear in the 3 coins. So in this case, I have 3 heads that appear. Over here, I have 2. I have 2. I have 1. There's 2, 1, 1, and 0. Okay, and what I can do then also, similarly, I'll do y. And y is the number of tails that appear. So over here, this is 0. Over here is 1. Over here, I see 1 there. Over here is just 2. 1. There's 2, 2, and 3. So now I can have questions like, trying to keep this all on the same page. Here's part A. I could do what is the probability that x equals 2? And over here, I'm going to do, what's the probability that y is between that y is greater than or equal to 2. Okay, so for part A, I have the probability of the x equals 2. So all I have to do then is to count how many times this occurs. Here it's for 2, there's 1, 2, 3. So it happens 3 times out of a total of 8. So it's 3/8. Now the next one over here, the probability that y is greater than or equal to 2 means that I need to calculate the probability of y equaling 2 plus the probability of y equals 3. Just as a reminder that the values that x can take on is 0, 1, 2, and 3. And the same thing for y. Okay, so let's do y equals 2, the probability that y equals 2. So I go down this one, I can count 1, 2, 3, so that's 3/8, plus I need the probability for y equals 3, so I need to count the number of times that this occurs, and this occurs only once, so 1/8, which means that it's 3/8 plus 1/8, which is 4/8, which is equal to 1/2. So what we should do is we should have a little English statement to convey what we have done to people that may not know probability, maybe this notation. So to express this, what I'll say is, so this is the probability, so I'm just reading this out, the probability of 2 heads appearing when 3 coins are tossed is 3/8. Similarly over here, I'll say the probability that, so in this case it's 2 or 3, and not heads but tails, when 3 coins are tossed is 1/2. Okay. This is page 7. page 8. Okay, so now just kind of as a little review, what we've done here is that this is the probability that the random variable x, whatever you've defined it, that's interesting, so again, that's the probability that the random variable x is equal to some value. Now we move on to something which is called the expected value. And we usually then, so we take x and we write it with an e. And what we kind of say with this is that it's like a measure of central location for that random variable. And what this actually means then is this what value x do we expect from the random variable x? Okay. So, for instance, people such as gamblers are quite concerned about the expected value. If a gambler is playing a game where he expects to lose 25 cents on each dollar he bets, he might not consider that the game is fair enough to play. But if he expects to win 25 cents on every dollar he bets, the game might not be fair, but it's now in his favor. We use the expected value to help us gauge our expectation of the experiment. What we express the expected value as, just a second, it's what we call a weighted sum. And you can almost think of it sort of like an average. What this is that it's the value of x times the probability of x, and then we sum for each value of x. And that's what this is saying up here. So this might not look very nice as a formula, but it's just our condensed way of writing it. What we can do then is, here's my example I'll use with the 2 dice. We said that x is the random variable of the sum of the 2 dice. Okay. I'm just going to write that out. So we had 2, 3, 4, 5, 6, 10, 11, 12. So over here we had 1 in 36. I know this is where we had the most probability, and then it decreases. So 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. Okay. What this is saying is that it's the expected value is equal to the value of x, so in this case it's 2, times the probability, which is this one up here. So the value times the probability. So there we've done this for when it's x equals 2, plus I have the value of 3 times its probability, which is 236. Over here, this is 4 times its probability, which is 3 over 36, plus 5 here is 6. Nine. Sorry, it's tedious, I know. There we go. So I've written that all out. Okay. So we have this over 36. So I have 2 times 1 is 2, plus I have 3 times 2 is 6, plus 4 times 3 is 12, 5 times 4 is 20, plus 6 times 5 is 30, plus 7 times 6 is 42, 8 times 5 is 40, 9 times 4 is 36, 30, 22, 12. Okay. Oops. So when we add that up, you should get 256 over 36. And the nice thing about that, 256 divided by 36 is 7. So what does this mean is that we expect that the sum of two dice to be 7. It also so happens that it's the highest probability in this case. But again, if we throw the 2 dice, we'd expect it to be 7. Okay. Let's move on to the next one. Okay, so let's talk about when we're starting to gamble, or even in maybe we think of life insurance. So here, let's think about this. We have the game value is equal to, let's say, the prize value times the probability of winning minus the cost to play times the probability of losing. So you can already see that this is very similar to the expected value, because here is kind of the value times the probability of something. And we could have written this as plus, and then we would have said that the prize value would have been negative to account for the cost to play when we lose. So they say that a game is fair is 0. Otherwise, it's unfair. Okay. So those are the two terms. Okay. So let's do an example of roulette. Again, it's that wheel that has 38 compartments. It's a wheel. Something like that. You spin the wheel and you throw a ball. And again, there's little compartments that the ball can fall into. There's 38 of those. So like a little ball will fall into it, say like in here. And that compartment would be labeled. So there's 38 of those. Okay, and they're numbered 0 through 36. And they also have a double 0. So there's your 37 plus the 1 gives you the 38. So the wheel is spun, and then a ball lands, comes to rest in one of those compartments. The gambler wagers, let's say, $1 on a single number. There's two things that could happen. So he could win, where he'll win $35. And if he loses, he loses that $1. Okay, so what is the expected winnings of the gambler? Okay. So this is kind of all of our information. There's the whole problem. So here's our solution. Again, we're going to use this idea of a random variable, and we're also going to be using this idea of expected value. So for this, what we'll do is we'll let x be the random variable of the player's winnings. Okay. So in this case, we have well, here's the question I should ask. What are the values of x? Just in the chat, what are the possible values of x? Anyone in the chat? What are the possible values of that random variable x? That's for Hugo that's in the chat. No, those are probabilities. But what are just the values of x? That's right. You can have 35 and you can have -1. So what we're really wanting is, what is the expected winnings of the gambler? Well, it's the expected value of x. So we have the values, we have 35 times the probability of x equals 35. Yes, exactly. Plus, now I'm going to put plus, and then the value of x, which is -1, times the probability of x equals -1. So just move this up. So over here, the probability of 35, the probability of winning is 1 in 38 in this case, which is what Hugo had said. So 1 in 38. Okay. And over here, it's a -1, where he loses $1. And that happens, well, it's the complement. So in this case, it would be the probability of him losing $1 is it doesn't land on the one that he has picked. So it should be 37 out of 38. Okay. So you get 35 over 38 minus 37 over 38. This isn't looking good because I have 35 minus 37, which means that it's -2 over 38. And that is approximately equal to, if I pull out the calculator, here we go, 2 over 38. Oh, I won't say, yeah, approximately -0.0526. So what this is saying is that the gambler for every $1 he wagers, he should expect to lose 5.26 cents. Yes. So you can see how the casinos have set this up, that they don't win, they win on average. So they're just, it's a very small amount. Every dollar that's wagered, the gambler expects to lose the 5 cents, and that goes into the casino's pocket. Now that's what the casino also expects. Every time a player puts down $1, the casino expects to make 5 cents. And you can see, just by the way that they have picked it, the $35, you can then play with how much money the casino could expect to win over the long run. Okay. So let's just kind of try that. Suppose the casino changed the rules. Let's say they only win 30, let's do $34. Well, then we can actually repeat the whole calculation. Same thing again. We would let x be the random variable of the player's winnings. Again, the values that it could take on is now not 35, but it's going to be 34. It's still going to lose $1. And so you can do the expected value again. So you have 34 times the probability of x equals 34 plus minus 1 times the probability of x equals minus 1. So the probabilities haven't changed, but the amount has. So we have 34 times 1 in 38 minus 1 times 37 over 38. So you have 34 over 38 minus 37 over 38. So 34 minus the 37 gives you minus 3 over 38. And so I'll pull out the calculator again. So 3 over 38. So this would be approximately negative 0.0789. So just lowering it just a little bit. Yeah. So in this case, again, it's in the negative. The gambler expects to lose 7.89 cents per dollar wagered. Okay. Well, that's the end of our lecture for today. I hope this has been interesting. If you want to get a head start on what I'm going to talk about tomorrow, we're also going to talk about life insurance policies. Example 9.3.4. And that's on page 405. We don't do any. Okay. Well, that's the other thing too, is it's an expected value. So again, if you have to round, it's like the average or expected value of children in Canada is, I thought it was 2.5, and it's very hard to find a half a child. So it gives us an idea of where the value should be, but it may not be the value that is possible to obtain in real life. Okay, and again, thank you everyone for tuning in. Have a great night. Perfect. Thank you everyone. Good night.